Okay, good morning to everyone. We'll resume now our sessions with Professor Barbara Osimani from the University of Munich. And, sorry?
Ancona, actually, in Munich.
Munich and?
Ancona.
Ancona, sorry. I didn't have that. And the title of her presentation will be Statistical Evidence in Strategic Environments. Okay, as usual, 4 minutes for the presentation and the rest for the debate. Thank you.
Thank you. So thank you for the organizer. I'm really happy to be here because I've been a little bit dealing with the evidence in legal settings when I was doing my PhD, but then I'm starting now with a PhD student who I have in Ancona who's really interested in this topic, so I hope that collaborations will emerge. So right into the topic. I'm interested in evidence, especially in how we assess evidence in strategic environments where there are conflicts of interest, vested interests, and uncertainty of various kinds. So the motivation, everything started with this sentence found in a paper I read while doing my PhD. It said, it may be unfair to invoke bias and confounding to discredit observational studies as a source of evidence on harms. As you may know, in medicine, the gold standard are RCTs, randomized controlled trials, or randomized clinical trials, exactly because they are putatively isolating your causal connection between the cause and the effect. And they are getting also the asymmetric relationship. So they are the gold standard for getting causes out of associations. So observational studies are not supposed to be able to deliver you this information. That's why RCTs are above observational studies in medicine. Now, why do these scholars assume that it would be unfair, that is not only mistaken, it is unfair, so unjust, to discredit observational studies as a source of evidence on harms? So I started to think over this asymmetry. Why, for efficacy, we need randomized controlled trials, whereas for the harm, we may be content with observational studies. There are several reasons. There is a high default prior for an undefined risk when we put a drug into the market. We know that we have not discovered all the latent risks which may be produced by this drug yet. And there is a higher risk for false negatives than for false positives regarding harm, because the drug has been developed and tested for a specific intentional effect, but then it will produce many, many different side effects, collateral effects, which we don't know about. And the risk-benefit balance and the precautionary principle tell us that we shouldn't be certain that the drug causes harm before making decisions. We can be also a little bit uncertain about that. Cumulative learning and the breach of probabilistic versus categorical cause assessment. Since we get signals regarding this harm from nature spontaneously, we want to be able to put together these different signals, which may not be orthodox evidence, in order to come as soon as possible to a decision about this drug. And we want to integrate all our evidence, not only prima facie statistical evidence, but also theory, knowledge about similar drugs, clinical case studies, whatever we have. And the issue of impartiality with regard to the false positives, false negatives risks. David Teyra, who's a philosopher that many of us know here, defended RCTs regarding medical decisions for drugs, with the motivation that they guarantee impartiality. So impartiality is characterized by him as a quality of a statistical or scientific procedure that allows no party to exploit the uncertainty regarding, for instance, the causal inference. However, if we would allow only RCTs as evidence for a decision regarding drugs, then we would be exactly partial, because a lot of people would die before we could decide that a drug can be retired from the market or not. And indeed, drug agencies do not decide on the basis of RCTs with respect to harm. The point is that we, as philosophers of science, should provide the justificatory basis for decisions which are not made on the basis of the gold standard. And regarding the fairness issue, The point is exactly regarding impartiality that medicine and pharmacology deal with specific kinds of products. These are credence products, and credence product is a technical term in economics for denoting products whose quality cannot be evaluated by the consumer prior and sometimes not even post consuming it. And this asymmetry, this kind of information asymmetry regarding the product also regards the evidence about the drug. Evidence about drugs are produced by the pharmaceutical industry mainly, and even drug agencies with which I work. They cannot be aware about all the data generating process which is behind the production of such evidence. And there are pressing ethical dilemmas, juridical dilemmas, and there are very high stakes in health, as there are in legal settings. The producers of medical knowledge often have vested interest in the research outputs and dissemination, leading them to engage in strategic behavior, which obviously exploits all of the above. So this is a little bit all the motivations that are behind our project. And indeed, there are institutional instruments to counteract this exploitation of uncertainty. First of all, evidential standards, such as evidence hierarchies, which, however, in the case of harm, have the risk to counteract against their very main purpose, deontological norms, decision rules. Now, regarding all these issues about harm and evidence and all these vested interests and conflicts of interest, all the dimensions of evidence which impact the assessment of evidence, also statisticians like Andrew Gellman and others are advocating for a more comprehensive view of evidence, where all these dimensions can be incorporated and tracked. Regarding drugs especially, the European Parliament is advocating for new instruments for putting together different kinds of evidence, but the methodological basis for implementing such a policy are shaky. Why? Because cause assessment of adverse drug reaction is still parasitic on guidelines which have been developed in order to test efficacy, and they fell short of using sporadic, fragile, and heterogeneous evidence efficiently. Sounds familiar to legal theorists, doesn't it? The point is that if you have a statistical model, viable distribution, Gaussian distribution, you can expect a certain likelihood of obtaining a certain evidence output. So you can regiment your evidence in your statistical calculation and deliver a posteriori your hypothesis. However, in the case of legal settings, or in the case of this lower level evidence, such as clinical case studies or molecular behavior and so on, you don't have such a protocols into which you can put your evidence and calculate how much it confirms your hypothesis. So what did we do? We tried to think about how the people reason about evidence in these settings and to formalize it in some way. So we developed the theoretical framework for justification of probabilistic confirmation of causal hypothesis on the basis of all the available evidence, which we termed e-synthesis. And I will come to this back, but this is the main output. You can see here, this is the causal hypothesis. Does this drug causes this side effect in a specific population, in a specific causal structure? So this is can be expanded. And these are indicators, abstract indicators of causation, imperfect signals of causation, such as probabilistic dependence, dose-response relationship, rate of growth. Dose response is whether there is a dose response, so more data points, more for multivariate variables, and more than binary, I mean. Rate of growth is a steepness of this coefficient possibly relating the drug to the side effect. Mechanisms, time, precedence, possibly other indicators, such as various asymmetries in the data. Difference making, this we consider a perfect indicator because difference making is about whether a variable makes a difference to the other. And so this is an asymmetric relationship. And so it's a perfect indicator of causation in our framework. So this tries to put together all the philosophical theories on causation, where in general the debate across different philosophers of science is what are the truth conditions for causation, and so they differ. We allow to relax truth conditions and to have just imperfect indicators of causation. So you might have in your body of evidence just one data point, or here, just one study, a clinical case study or a molecular result, I mean a basic science result. And this would be a report feeding into the the mechanism node, which feeds into the causal node. Why are these errors in this direction? In some sense, this is an epistemic network, but it represents the causal structure of your epistemic environment. What does this mean? You presume that if there is indeed a causal connection between the drug and the cause effect, then this would cause these abstract indicators to hold more likely than not. And consequently also, if you presume, for instance, that there is indeed, let's say, a difference-making relationship between the drug and the cause and the side effect, then it will be more likely than not that you will find a positive report about difference-making. And this holds for all the possible abstract indicators. So these rep nodes represents concrete study results, data, which, however, of course, themselves imperfectly reliable. They are affected by random error and systematic error, any kinds of error. And these kind of error are represented by these nodes, the reliability node and the relevance node. Relevance is about external validity. Reliability is about accuracy, bias, systematic error, random error. In this talk, I will exactly talk about reliability, about how to model reliability, which is something that we share with legal theorists, for instance. Okay, so 3 toy examples to introduce the paper. Formal models of scientific inference, Bowens-Hartmann versus Landes and Osimani, results and discussion. Okay, I will read them because they are not very easy to be read from the audience. So suppose you are a general doctor who needs to prescribe a therapy for a patient with an uncommon disease that you can pretty well diagnose, about whose most cutting-edge treatments you are, however, unaware. You make a quick search on PubMed and find out that a new treatment has recently been tested for this specific condition in 2 distinct studies. Since this is not your specialty, you do not know the people who do research in this area, how good they are at making research, or how biased they may be because of possible vested interests. Suppose the studies are of equal quality. That is, they have the same capacity to detect true positives and false positives. Would the 2 studies be more confirmatory for you with respect to the hypothesis of efficacy if they came from the same research group or if they came from 2 completely independent ones? Another example. Consider a court jury involved in judging a culprit for having committed a crime. They receive 2 forensics regarding the same type of evidence, hair material or blood or traces of genetic material, delivering some confirmatory support to the hypothesis of guilt. Would these forensics be more confirmatory if they, with respect to the hypothesis, if they came from distant labs or from the same one? Third example and last one. A governmental body needs to make policy decisions regarding the 5 next years of fiscal regulations. Before involving expert groups, they consult scientific databases and search for empirical data regarding various fiscal interventions in diverse countries, looking for evidence as close as possible to the historical and political situation they are dealing with, external validity. They find 2 relevant studies which investigated the efficacy of a given fiscal program and delivered evidence at the same significance level and power. Would they find the fiscal scheme more or less efficacious if the 2 studies came from the same source or from different sources of information? The answer is, it depends. Now the point of the paper is to show on what it depends and why. The things the answer depends upon are revealing of various essential forces in statistical inference, random and systematic error, which in turn depend on nature and standard. the interaction of these diverse forces has not yet received explicit attention. And I think there are analogies to, of course, the legal setting. The main intuition is that many aspects of implicitly or explicitly factor in when we assess evidence, and our task is to make them as explicit as possible, our Carnapian text. So this is a paper. Rationale behind varied evidence. Consistent findings from different routes converging to the same hypothesis are more confirmatory than if they came from the same one, since it is easier to explain this coincidence if the investigated hypothesis is true rather than not. So if we have one line of evidence converging to the hypothesis, another line of evidence converging to the hypothesis, this is more confirmatory than having, let's say, consistent replica in the same line of evidence. If it were false, one would need an alternative explanation for such coincidence of measurements. There is an analogy with testimonies. If we have detailed, consistent testimonies from different witnesses, then there are only three explanations. A coincidence, collusion, a common cause. They are telling the truth. But the point is, how probable is coincidence? How probable is collusion? How probable is common that it's true? Okay. The variety of evidences states that items of evidence from independent lines of investigation are more confirmatory, ceteris paribus, big ceteris paribus, than replications of analogous studies coming from the same source. I always like to quote Paul Mayle, a Lakatoshian philosopher of science and methodologist. Any working scientist is more impressive with 2 replications in each of 6 highly dissimilar experimental contexts than he is with 12 replications of the same experiment. But there is a variety replication trade-off. Indeed, there is an obvious marginal diminishing value in the epistemic gain provided by exact replications. I prefer varied evidence. However, what is interesting is that replications give you higher order evidence about the reliability of the instrument itself. If you test the same parameter with the same instrument more times, then an instrument gives you more or less accurate values around the same mean, I mean closer to the mean, then this means that the instrument is accurate. In statistics, the rationale that distinguishes the 2 approaches is exact replication, excluding chance results, and conceptual replication, excluding alternative explanations for what you found. Study artifact, latent variables, intentional bias. So what are exactly the parameters that determine these trade-off, and where should the curve lie and why? These are the questions that we try to answer with this formalization. Yeah, we did it also because there is a lament of formal methods to test replication, the informative value of replication in the market. So we try to do so. So we started with Bowens-Hartmann, who provide a model for a formal model for scientific inference that shows that variety of evidence may fail. Sometimes you would prefer evidence from the very same instrument. Their results, however, mainly rely on dividing the hypothesis space regarding the truth-tracking properties of the instrument in. The instrument is either perfectly reliable with a given probability. You don't know whether it is reliable or not. But if it is reliable, it is perfectly reliable. Otherwise, it is a complete randomizer. It is completely disconnected from reality. At the same time, if the instrument is a randomizer, it doesn't give you positive or negative results with 50-50 probability. It can also be 90% or 10%. And we will see that this is very important for their results. So how does the model work? Here we have the hypothesis, the scientific hypothesis, the unobservable, let's say, and this is an observable consequence of the hypothesis. Suppose that your hypothesis C causes E, then a possible consequence, for instance, is a difference between 2 groups in a randomized control trial. This consequence is not a perfect indicator, but the probability that the consequence holds, if the hypothesis holds, is P, and is higher than the probability of the consequence holding if the hypothesis doesn't hold, which is Q. So by assumption, P is higher than Q in this model. If the consequence holds, then an instrument might detect it and give a report about this consequence. the report is, in a given study, you find a difference between the treatment and the control group, for instance. So you would receive a positive report with probability 1 if the consequence holds and the instrument is reliable. With probability 0 if the consequence doesn't hold and the instrument is reliable. But if the instrument is not reliable, the probability of receiving the report is the same, A, parameterized by A, whether or not the consequence holds or doesn't hold. So whether or not the consequence holds or does not, the instrument delivers you 40% probability yes. So it says yes 40% of the times, or 80% of the time, without any connection to the consequence. It is a full randomizer, okay? However, you don't know whether the instrument is reliable or not. And the uncertainty about the property of the instrument is parameterized by rho, which tells you your uncertainty about the instrument being reliable or a randomizer. So what do they find? First of all, yeah, they apply this kind of setting to different situations. A situation where you test with the same instrument twice your consequence. And so you have, I don't know whether you can see it, but you have 2 reports here delivered by the same instrument. This is modeled by having the report nodes being shared by one reliability node. Of course, this is not a neutral assumption. And in the discussion, we will discuss all these things. Anyway, it seems a little bit like in structural equation modeling, where when the errors are shared, then there is a common latent cause. So it's as if there is the same instrument delivering you 2 reports. Here, the 2 reports are delivered by 2 distinct instruments, which is modeled by the reliability node, by having different reliability nodes for each report. Here is another setting. It is just one report for just one consequence against 2 consequence, 2 reports from the same instrument. And here also the variety of evidence phase, but we won't deal very much with this. Here is the third comparison. It's between here 1 consequence, here 2 consequences, measured by 1 instrument or 2 instruments. The point of having this treatment and control, let's say, setting is to see whether having 2 reports from 1 instrument or from 2 instruments, so from less varied and more varied evidence, is more confirmatory to the hypothesis ceteris paribus. Ceteris paribus means here, with the same conditional probabilities between the nodes. So with the same conditional probabilities between the nodes, would it be more confirmatory to receive 2 reports from 1 instrument or from 2 instruments? And the same here, from 1 instrument and from 2 instruments. If the variety of evidence thesis would inevitably hold, then we would have more confirmatory boost in this situation and in this situation. I'm leaving this aside because it's particular. But for some values of the rho parameter, the A parameter, the P parameter, the Q parameter, instead, the hypothesis is more confirmed in this setting and in this setting. Let's see which values and why. Well, let's do this, and then we shall explain it. I have to have the microphone. So I show you the space, the parameter space where the that fails. In the first setting, it's easier. So we have the rho A plane. What does this mean? This is the probability that the instrument is reliable from 0 to 1. And this is the parameter associated with the randomizing instrument, with how much frequency it delivers positive reports. So here, 0 positive reports, and then until 1, always only positive reports. Well, in Bovesato and in our setting, we only deal with intervals strictly between 0 and 1. Okay, so if the instrument is a complete randomizer, it delivers positive reports 50-50%. Otherwise, it can also deliver positive reports, with 25% of the times, 75% of the times, etc. Now, the that phase in this space, that is, when you think that the instrument is more likely to be unreliable, so to be a randomizer, and if, in the case it is a randomizer, it is less likely to deliver negative positive reports. So it tends to say no. Then, receiving two reports from the same instrument is more confirmatory. Can you tell me why? Because then, if you tell me why, then it's much more easy. So if you are more likely than not to think that the instrument is you have one instrument, or you have, and you are skeptical about this instrument. This instrument should be a randomizer. But if it is a randomizer, it is a naysayer, let's say. It tends to say no. However, you receive two reports from the same instrument, and they are both positive. What would you think? First of all, that it's less likely that it is a naysayer. So if it is not a naysayer, it must be the other kind of instrument. And the other kind of instrument is a reliable instrument. So receiving two positive reports in this area is more confirmatory if it comes from one instrument than if it came from two distinct instruments. And this is confirmed by the fact that this is for reports, number of reports equal to. And we discovered this exactly because then Bowens and Hartman had an unpublished paper where the area of that failure even increased. So row 5, 4, let's something like that. This is n equal 2, then n equal 4, then n equals 10, and at 1, n equal infinite. So the area of that failure increases in A. This means that until you think that the instrument is more likely to be a randomizer than not, even if you receive 10 positive reports from the same instrument, but the instrument, if you receive 10 positive reports from the same instrument, or from 10 distinct instruments, wouldn't it be more likely that it is more confirmatory from 10 distinct instruments? It would be. That's why Bowens and Hartman didn't publish. They didn't understand. But then, if you see at this, the increase of this area in A, this means that even if you are no longer a naysayer, but still there is some room for delivering negative reports, the more reports you receive, the more A is allowed to be higher. It's very, it took a lot of time to arrive to that, but the point is that if, for instance, let's look at the results in the graph here, because it's, then I will come back, yes, here. For instance, let's do 4. If you receive 4 reports from the same instrument, rather than from 4 distinct instruments, A can be even 0.61. This means it's not a naysayer, but still it has a likelihood to deliver negative reports. And so, because this likelihood is high enough, this tells you that the instrument is indeed a reliable instrument, not a randomizer, because the reliable instrument, if the hypothesis holds, would say always yes. That's the point. However, this runs against our intuitions about reliable and unreliable instruments. That's why we try to model the thing differently. So now I go on with the slides. Hopefully, okay. So, Bowens and Hartmann's randomizing instrument is a randomizer of a particular kind. If A is 0.5, then our unreliable instrument is a proper randomizer. However, if A is less than 0.5, the unreliable instrument tends to be a naysayer. And if A is higher than 0.5, the unreliable instrument tends to be a yes man. In an unpublished paper, Bowens and Hartmann find that the area of wet failure in the row A space increases with increasing n. Receiving several consistent reports from one single instrument is more confirmatory than receiving them from different ones for an increased number of consistent reports. This goes against the intuition of too good to be true evidence, and this is key to our explanation of the Bowens-Hartmann results. The area of wet failure grows in A. Sorry, so these are the... So wet failure in Bowens and Hartmann's model is mostly driven by modeling the unreliable source this way. If A is lower than 0.5, the unreliable instrument tends to be a naysayer. So the consistency of positive reports from the same instrument boosts the belief in the instrument not being such, and therefore in it being reliable. Therefore, we have that failure. Instead, if A is higher than 0.5, then our unreliable instrument tends to be a yes man. So the consistency of positive reports from the same instrument boosts the belief in it being reliable indeed, but it depends on how many reports you receive. This goes against our intuition about too good to be true evidence. If we receive always the same evidence deterministically, so we think that the instrument is biased. And so, because bias exacerbates error, so we wanted to develop an instrument that would take this into account. And we changed simply the parameters of the model. For us, for our model, the instrument may be reliable with probability rho, but it can be also positively biased with probability 1 minus rho. And this is important. In our case, we receive positive reports according to the following probabilities. If the instrument is reliable and the sequence holds, then we receive a positive report with probability 1 minus a random error, not invariably 1, like in Bowens and Hartmann. And the same for the receiving a false positive, a positive report when the consequence doesn't hold. So we have a false positive with random error I, epsilon minus. If the instrument is positively biased, we receive positive reports at a higher rate than if we received them from the, let's say, reliable instrument. And false positives, see, these are true positives, and these are false positives. Also, we receive them at a higher rate than if we received from the reliable instrument, which is affected only by random error. So to illustrate this, true positives are here. These are the true positives. This is true positive rate for the biased instrument, for the reliable instrument. And then here are the false positives. This is for the biased instrument and for the reliable instrument. So the assumption is that alpha is to the right of 1 minus epsilon and gamma is to the right of epsilon. Okay, results. In our case, also, that fails as well, but the area of that failure changes, and also the parameters according to which it fails change. And this is determined by this curve. The false to true positive rate of the biased instrument is lower than the false to true positive rate of the reliable instrument. This is the curve. So here that holds, and here that fails. Now we try to explain why. However, for, let's say, plausible values of epsilon and gamma, the that almost all the time holds. So this is a zooming in, let's say. And this is also for the third scenario. It's very similar. So that tends to fail with decreasing false positives and increasing true positives of the biased instrument. And at the same time with increasing random error of the reliable instrument. What does this mean? That replication is favored when the biased instrument tends to be more precise with respect to the alternative one. For very low values of gamma and epsilon, the instruments are believed to be precise, if reliable, and with very low bias if they are biased. Hence, testing through different instruments is more confirmatory, the area where the that phase becomes negligible. When evidence is highly biased for the biased instrument, so gamma much larger than epsilon, then hypothesis confirmation is greater from varied evidence. Here we have a high suspicion of positive results being false when coming from the same instrument. So a consistent series of positive reports is more confirmatory when coming from the independent sources. That holds again. Now, for high values of gamma and epsilon, both instruments tend to be sloppy and unreliable. The VAT fails in this case whenever the ratio of false to true positives is lower for the biased instrument, because two consistent reports from the same instrument increase the probability that they are true positives, via increasing the probability that they come from the more precise instrument between the two. It is biased, but it is more precise. So if they come from the same instrument, they are more confirmatory. However, I mean, this is a discussion part. There are a lot of assumptions here. I mean, let's talk about the positives, first of all. So beyond the mathematical results, this research leads us to be aware of analogies and disanalogies between natural epistemology, epistemology of knowledge acquisition in ordinary settings, scientific setting, and legal settings. So we have to be aware about the causal blanket behind acquisition of evidence. By providing a template on which to discuss different ways to conceptualize reliability, different models of inference, how to model the diverse dimensions of noise, what does independence of items evidence mean? Now, assumptions. We have modeled inference through Bayes nets. And so the relations between hypothesis and evidence is governed by the Markov condition, faithfulness condition, sufficiency, in the sense of causal sufficiency in the Peirdian sense and Gilmore sense. Do these things hold in the settings that we are investigating? Yes? No? And the point is also that we have a specific causal blanket leading from, I can write it here, hypothesis to consequence to report, and then we have the instrument represented here in some sense, okay? But this is not the only possible way to formalize the scientific inference, of course. For instance, one could also model bias by having the error between the consequence and the report being removed, so that you're not measuring what you're seeing is not what the nature signals, but only what the instrument gives you. And indeed, the way that Bovens and Hartmann modeled the unreliable instrument de facto removed this error because the randomizer is not connected to the consequence. So in some sense, even if they draw this kind of causal blanket, in the case of the randomizer, it's as if you remove this error. So the interesting point, according to me, to develop in the future paper is your uncertainty is not only about whether the instrument is reliable or not. The instrument should be considered as the entire data generating system and the causal structure of this system. So your uncertainty is about how the evidence is generated, what are all the causes of this evidence, which may be not only nature, the sender, the instrument, and so on and so forth. Thank you.